Professor Wray, can you let us know when you're ready?
Oh, sorry, I'm not getting sound. Sorry. There we go.
Hello. Can you let us know when you're ready?
I've just got to.
I have a great pleasure to introduce Professor WrayBuntine. He is a professor at Monash University, where he founded the Master of Data Science and is director of the Machine Learning Group. He was previously at NICTA at Canberra, Helsinki Institute of Information Technology, NASA Ames Research Center, US Berkeley, and Google, as well as various startups. He is known for his theoretical and empirical work in probabilistic methods for document and text analysis, social networks, data mining, and machine learning. He is on several journal editorial boards and has been senior program committee member for conferences such as IJCAI, ICLR, UAI, ACML, SIGD, GKDD, and ENNLP. He has over 200 academic publications, several software products, and 2 patents. Professor Wray will tell us today about, I lost your title of your
dealing with information overload.
Dealing with information overload. The floor is all yours, Professor Wray. We're looking forward to hear what you're going to say.
Okay. I'll do the share. I hope we're all good. Now, this is about 10 minutes of a career perspective, and then I'll head to the main talk. The main talk itself has a part of it is just set up, talking about a major problem, discussing the issues, and then the second part is drilling down to a very specific problem. So a bit about my career, and I'll be try and fly through this. So I've been to a few countries. Australia started out, UK, United States, 5 very interesting years in Finland, and then back home to Australia. Some of that was in big labs, a bit of time in startups. Academia, I entered in quite late when I came to Monash. It was a bit of it in Helsinki, but only part. I was dealing with my family in the early 2000s. My wife had a lot of health problems, but that's all finished now. So I'll tell you a few stories of some of the research I've been doing. The first part, which grew out of my thesis, was Bayesian model averaging. I quickly ran into some folks who were doing a similar thing. David Madigan is the big professor at Columbia now, but he was like me at the time, just starting out. Leo Breiman was one of the local guys. If he's the famous statistician who invented random forests, which any good classification person should know if you play on Kaggle. He was a good friend of my boss, and he didn't believe the results I was getting. So eventually, after a couple of years of trying, he eventually came up with bagging and invented random forests, which beat my algorithm. But that then became the top algorithm for about 15 years until XGBoost came along. Very recently, we revisited all of this work, and we did Bayesian network classifiers with some fancy smoothing technique and ensembles. We put that together, and we're matching XGBoost. Why is that important? XGBoost is the best supervised classifier on the planet for typical tabular data. It's not something we use for image or text, but it is the best for typical tabular data, and we're getting about the same. Amalgamating the various techniques I'd done here in the past. So another area I did was what's called Bayesian non-parametrics. The field was really started off by Wray, who's one of those amazing geniuses who's now based at DeepMind in London. And for about 5 years, Michael Jordan had introduced the technique to the world, and for about 5 years it was rife. It was everywhere, and people were doing it all over the place. We got onto it a bit late, but we looked at it and we realized you could do it with something called a collapsed sampler, which is a bit more technical, and it comes from the statistics community, but it actually worked a lot better, and we figured out you didn't need these techniques, and most instances where people are doing this can be substantially improved using the sort of techniques that we were doing. We weren't the only people that came up with these, but probably we were the earliest ones. I maintain a strong relationship with Lancelot James, who was actually the guy who taught UIT how to deal with these problems, and so we're still working together on this. I'm just going to show you this because it's just so weird. This was a famous I was told it was a famous proposition. So Lancelot James had told me this is the most important bit of theory you're ever going to see, right, in this area. And he'd always scared me. Oh, it's so complex. He'd always scared me, and eventually, after a couple of years, I decided to go and study up what all these terms were in statistics. And it's very mathematical. It took me a couple of days to go through the literature and to figure out what all of this meant. After I'd figured it all out, I realized I'd proven the very same, exactly the same result a couple of years earlier. So Lancelot had been scaring me with this proposition. It's so important. You've got to study it. You've got to study it. Oh, I can't understand it. What is it? I'd proven exactly the same thing a few years earlier. But the mathematical descriptions were so different, so foreign, so unusual that I couldn't figure it out. Anyway, this is just showing you the two communities, the official Bayesian non-parametric community and the machine learning community are so far apart. Anyway, this is sort of what I've been doing for those years: trees, Bayesian networks, forests, which is where Leo Breiman's work came in, hierarchical, and non-parametric. We put non-parametric on there, and that's how we do smoothing. So the other thing I've been looking at is probabilistic programming. And if you like, this is the statisticians attempting to do what the deep learning people did. So you can look at PyTorch, TensorFlow, all of these things. The statisticians had their own sort of versions of this, trying to work this same similar idea, automating machine learning, in a number of tools, like Stan is the best known example. But I've been working around this for a while. We've recently done some more work on it, 2021. So I'm still looking at this a little bit, but it's not a main area. But this is what we're talking about today, information overload. So I got interested at this when I was at Google briefly for about a year before I went to Helsinki. And we ran a related project in Helsinki, a big EU project, some local Finnish projects. Very interesting time. And we got back to it when I was at NICTA, and also recently at Monash. And now we're looking at a bag of a number of technologies, which you'll see in a few slides, to address this problem. I'll talk about the problem, and I'll talk about some of the things we're doing to address it. But for me, this is one of the big problems presented to us in the in our community, and certainly the medical community has their own version of this. So that's basically the career outline. Now, quickly, so what am I doing at Monash? Director of the data science degree. It's a very big degree. We've had a bit of a shrink due to COVID, it shrank by half or more. Director of Machine Learning. So this is our machine learning group at Monash. There is some 25 faculty of various kinds, professor down to junior faculty and postdocs and what have you. We've got quite a lot of PhD students in there. This is more an administrative role, I should add. I do a number of things, but one of the things I do is support my junior faculty and my students. We hold information sessions. We support their research. I've currently got 9 PhD students, having completed 16 so far. And these are the 3 subjects I teach: statistical modeling, semi-structured data analysis. This is our latest unit we've introduced. Very interesting. The students love it. It's natural language processing and graph neural networks kind of put together. 2 fabulous areas and very exciting stuff. It's great to teach it. Okay. A bit of community work. European Conference on Machine Learning. A decade ago, I did a bit of work for them. Now I'm working a lot with the European Conference on Machine Learning, and we do very note that we haven't had a representative. We haven't really had a big play with the over your side of the world. So this is something we need to be looking at in the future. I do love tutorials, so I've given quite a few, and we've just started up a new tutorial series. I'm on the steering committee for that with ACML. I do a lot of sort of senior reviewing this is and conferences as grants as well. So let's start on what am I currently doing in terms of research, and all of these research areas, they're all service areas, if you like, for information overload, right? The big picture that we'll be talking about later. So Bayesian interpretation of deep learning. In our information overload problem, we've got a lot of different things we have to do. And when you're putting together a lot of different technologies, you really need, I think, a sort of an overarching principle. How do you figure out, how do you put together competing ideas? How do you configure things to think of the right technology for a particular problem? Well, for me, that is the really probabilistic or Bayesian, if you like, and it helps us understand and interpret different techniques. And deep learning has had a massive build up in the last couple of years. Huge difference in capabilities. Data augmentation, massive improvement in classification using this. It's got a wonderful probabilistic interpretation as a convolution. And that's very insightful when you see that. Semi-supervision, which is changing a lot, actually, how it works. The old techniques are probably no longer used. Self-supervision, and this is where we have things like BERT or pre-training. Pre-training is how you win any image or text classification problem these days. If you're not doing pre-training, you won't get anywhere near the good results. And it's recently, I figured out a year ago it was pseudo likelihood training. And I think recently, I think it was a Facebook group, did a big paper on that and showed they could get improvements. Pseudo likelihood is one of those wonderful techniques that we use in statistics with a long history, and it's something I love to do. Knowledge distillation, very important. Boy, we do a lot of this, but meta-learning is a recent thing now. Meta-learning was, I think, the number 3 workshop at recent NeurIPS, so it's a very big area. Graph neural networks was the biggest 2 years ago. A year and a half ago, graph neural networks was the biggest. And graph neural networks is kind of related to natural language. in some of the technology they use, actually. But meta learning is number 3 in terms of big interest, and it's a very good technique. We view that as hierarchical Bayes. Great way of understanding it. There are some other techniques going on. I've never been convinced really that adversarial methods are. I'm pretty sure they're just data augmentation, actually, from what I've seen. Not really convinced or anything else, but that's something we have to see. So that's how, and all of these things we need to use. We need to know these things in order to really do state-of-the-art techniques for the various tasks we have to do in our information overload problem. We're also using the social media task as it's a good way of, it's a simple, smaller task, and it's where I get a lot of, we get a lot of local interest in this. We did a study on COVID-19. We're currently doing a study on Australian politics, and the right to be forgotten, if you know the GDPR in Europe. We've done a study on that. So, but this is very interesting applied work, because you get to see a big difference between what the applied people do, what the empirical people do, and the empirical people, the people who think they're applied, but they're actually publishing in the, say, natural language or the machine learning literature. But if they're not actually publishing in the application communities, in many cases, it's not really applied. And there's usually a difference in requirements in the two communities. It's very good to see that difference. So let's start looking at this information overload problem, which I've been alluding to. I'm sure some of you feel like this when you sit at your desk and look at all the things you have to read. Certainly it's a good characterization of how I feel sometimes. There's way too much information out there. Why is that? Well, the internet society, it's everywhere. Corporate data all over the place. Bibliographic data, that's one of my big problems. There's too much of it. And of course, it's no longer just simple things like text. Now everything is structured. Networks, graphs everywhere, graphs and text. That's why we put those together in the one subject that we teach. And this is what you get. If you do a Google search on information overload, they give you all of these fabulous images people have put together to illustrate the idea. So there it is. And in academia, this has its own impact. Here are some big, famous, top-notch academics complaining basically about the impact of information overload. And I'm tired of finding papers that are special cases of what we did many years ago. You know, any senior academic should understand this problem. But really, it's happening more, and it is an impact of information overload. There's so many papers. How can they expect to see yours when there's, you know, you may be calling it a different thing, actually. So I'm calling this the academic singularity, as sort of a reference to the technological singularity, which is a theme from the Big Bang Theory. So in the Big Bang Theory, so when does machine intelligence catch up and overtake human intelligence? You know, that's the issue. Well, we have that problem in our academic research. You know, there's so much academic research out there. It's swamping us so much. At some stage, we're going to need automation, AI, to help us do our academic research. There's way too much of it to keep up with everything. So that's really what this is about. We need to apply AI to support our own research because there's too much of it. The publication cycles are now so quick, so quick. People put their paper up on Archive or somewhere else, and it's already old news by the time you get to the conference. You get to the conference, and I've seen that, saw that 6 months ago, not interested. Many people rediscovering the same things. In fact, I tell my PhD students, if they've been working on an idea and then they find that some famous person published it 6 months ago, I tell them, great, you're onto a good thing. You've really caught up. You're now worthy of a PhD. If you can create an idea that a famous person has already got to 6 months ago, that's it. You're good enough to probably to complete a PhD. So, but that's all related to this overwhelming amount of research we will get. So let's look at how we put together the sort of previous and related information on information overload. So what have the information retrieval people been doing in a broader sense of the word? Well, a key part of that community are the systematic review people. And hopefully some of you have heard of that term. That's how the medical people do studies. And the medical people have their own version of what I'm calling information overload. And the idea is a lot of different medical groups study a similar thing. They will get different results. And so they want to do a systematic review, assess the literature, and come up with a consensus. Come up with what they think is a state of the art from all the different publications on the same problem. And they've got all sorts of software and they're doing research in this. Generally, though, they're not up to deep neural networks. So the technologies they're using satisfy a lot of things they need, duplicate detection, things like that. But it's only recently that and this is a good example of that, very recent, right? Just a month ago, these guys are starting to use word embeddings and classifiers to do their find me similar papers task. And this is 3-year-old technology now. So it's 3 years old for us. They're just starting to apply it into this problem. I always say Google Scholar and Semantic Scholar are similar to help us deal with information overload, but they're not personalized. They're really these guys are really operating at scale. The Google Scholar team is about 4 people. It's not a money winner for Google. They do it as a service to the community. And what's really going on is that in recent years, state of the art information retrieval is deep learning. So Google, for instance, apparently is currently putting some of that BERT-style recent NLP research into doing efficient versions of it and trying to get it down into their search engine. But when I talk to the IR people, they are focused in a very different way. They really want, and this is what Google has. Google has something that only a few other companies do. Baidu, Yandex, Bing. They're the only people who have massive collections of search terms and documents. None of the rest of us can get that. So they can build their search engines to do a match using this kind of data, but we can't do that. Anyway, what's the state of natural language processing? Where are these guys? Again, massive changes in the last 5 years. It's all transformer models. And I mentioned the term BERT earlier, which any of you have heard of that. They're called bidirectional and left to right encoders, decoders. If you haven't heard of these, look at some Hugging Face is the dominant platform for that. But Alan AI has some great demos that I always show my students. But really, a lot of the sorts of problems that we address in our information overload task, state of the art using these techniques. If the state of the art for these problems is not using these transformer models, then it's using the output of the transformer models as the input to their first step. So it's using it invariably. There's another technique that we need to do our work that's really coming out of deep learning generally. When we build a classifier for supervised learning, we need a measure of confidence and uncertainty. We need to say, is our classifier really happy with this particular result here? Is it uncertain? Is it, does it lack confidence? So you can say, what's the outcome of tossing a coin? You'll say, well, at 50%. Why? Because you have no idea. 50%, absolutely no idea. Whereas you can be a doctor and I could come into an office and they could say, what's the probability that I've got flu? And they're going to say, don't know, 0.1. After they've tested me out and done all their evaluations, now they'll know. They'll say, oh, I'm pretty confident. It's 0.95 and I'm certain. So your confidence of your predictions changes as you get more information. We need to measure all of these things. And there's some recent technology for that. So these are the two critical technologies we're using in all of our work. But let's briefly talk about these different tasks. And these are how we do address information overload. We need to break documents up into bits. If your document is too big, it's confusing for search. Key phrase identification, very important for labeling, really, and for informing users what are the key things of this. And people, authors, are terrible at this task, always. They always do a bad job, a poor job, generally. They miss a lot of key phrases. Topic extraction, what are the topics in there? And that can be used for visualization. Summarization, you want to have a précis. But one of the key technologies we're using is something called active learning, which I'll talk about next. I'll drill down into that. And of course, information retrieval I'm talking about. But we want to speed that up and sort of make it more suitable for the personalized system. So let's talk about this particular task, active learning, which we use for personalized information retrieval. And here's a general way of describing it. This is just a fabulous figure I've got off this website and I couldn't beat it, so I'll use it. You do a search on Google, Flickr, get some images. But what you want to do is build a classifier for bicycles, an image classifier, but you don't have a bunch of tagged images that have bicycles in them. How are you going to get those tagged images with bicycles? Well, here's a way of doing it. You'll select a bunch of candidates. You'll pay someone to tag them for you, and they can circle where the bicycle is or toss out the images that don't have bicycles. So you pay people to actually annotate the images for you. And once those images have been recognized, now you can run your image supervised learning algorithm to train to recognize bicycles. You can't train to recognize bicycles if you don't have a lot of tagged images. So this is the task. And what are the two bits that matter? How do we select the images? We want to select a smaller number of images to give to our annotation people. And certainly if we're learning about bicycles, we don't want to give them thousands of images that don't have bicycles. So we want to be selecting carefully what we're giving them. Secondly, these are the people that matter. Now, if we're doing bicycles in images, we can pay people in Mechanical Turk. But if the task is does this person have lung cancer, looking at their chest x-ray, we can't use Mechanical Turk for that. We can't ask someone off the street, hey, has this person got cancer? They have no idea. You've got to pay highly trained, expensive professionals. And the way we joke about it is, well, you know, we can go and ask our medical specialist, what do you want to do? Do you want to spend 4 hours marking up some images for us and tell us where the lung cancer exists? Or maybe you can go and take 3 patients and earn enough money to do a holiday in Switzerland. You know, they're the options, really. It's really hard to get data out of medical experts, is what I'm saying. So we really have to, if we're going to be getting data from them, we have to be very smart about what we're showing them and really try and optimize the interaction with them. So that's what active learning is about. Clever selection of examples to really try and speed up the learning. Now, here are 3 real application scenarios that use active learning. So I've given you a sort of a description of what it is, but here are the cases where it really matters. The first is learning with less labels. And there's actually a DARPA project on this. DARPA is the American military research agency. Why do they want? You just imagine there's some general somewhere who says, oh, you know, if we can just give you a couple of images of Russian tanks and then we're good to go. We'll have a classifier that'll automatically spot them from satellite, you know. So that's what they're thinking. They want to be able to spot things in a military situation with very little labeling. Personalised IR, this is the problem we're looking at. Annotation. So this is a typical social scientist thing. It's also a medical thing, a psychologist thing. You might want to look at people's notes. You might want to look at police reports. And you want to mark up, okay, where in that report are they discussing a potential suicide situation? Where in that report are they discussing that an individual was thinking about self-harm or thinking about taking a particular drugs? So you've got an annotation task. The actual paramedics or the police or the emergency personnel, they don't have time to mark up their documents. They can't do that. So instead, we pay annotators to do it. And we have to feed the annotators with our best guesses and put that into an active learning scenario. But nevertheless, you want to get as many cases as you can of this kind of data out of all the reports you get in order to build up a good database on the problems. So that's our real life active learning scenarios. A bit of history. Really, it was started up by my old colleague David Lewis when he was at AT&T. The technique called uncertainty sampling. I'm going to say this is a lousy technique. It was good years ago, but it's not that good now, even though people still use it. Recently, there's been a bit of theory that we've been looking at. MOCU is the phrase. It basically fixes some problems with uncertainty sampling. Some guys at Oxford, Cambridge, yep, did this, something called BALD. As it happened, I'd done this theory about 10 years earlier, but I never published it. It was all, I didn't have the means or interest, but it's not bad, but it doesn't work that well. And if you really want to find out what's going on, to really understand things in deep learning these days, you've got to go to surveys because the field is moving too fast. You find a survey that's only a year old and you can catch up a bit. And this is a good survey on active learning done a year ago by one of my colleagues actually here. It's a good one to catch up on these things. So we've been looking at all the empirical work people are doing. Usually they don't run on many data sets, usually only 3 or 4. They run on very large data sets, and that's no good for us. We want small data sets because, you know, that's where personalised information retrieval is. It's also where the annotation task is. They don't have the money to have experts label 10,000 things. They also do big batch sizes in their active learning. So in this loop here, you can pass one at a time to the annotators and then retrain your model, or you can pass on 100 and retrain your model. And when you pass on a lot, that's called batch active learning. So people use different batch amounts, but they've never really explored the different issues involved. Imbalanced data, data with where you've got quite low abilities to predict. So for instance, sentiment is a lot harder than, say, topic, usually in text. So in our view, there's a lot of questions left unanswered, and really difficult to make comparisons between the different published literature because of the huge diversity and the lack of standards. But also the evaluations are almost always wrong for us, right? They're always doing minimum errors. And in our scenarios, minimum errors don't figure. It's not, doesn't come anywhere. Here are our scenarios. Minimum errors never matters. For personalised IR, we want high recall. For annotation, we want high recall. And generally, for learning with less labels, the problems that matter, rare classes, and accuracy is no good. You want high precision on the recall you have or something. So minimum errors is not the evaluation metric that matters in the problems we're addressing. So we're saying, well, this empirical work ain't that useful. So we've started looking at things again. We decided that just to really understand the problem, let's start off with a batch size of 1. And that means a lot of the current techniques we can't really look at. And we're particularly interested in active learning for text, of course, that's what we're doing. Most of the active learning has been in images, and their methods are quite different. So we're using the transformer BERT style text classification. We're doing ensembling to get our confidence and uncertainty out. And for the sorts of problems we're doing, these are the data set sizes we're dealing with, not the 10,000s that you see in a lot of the literature from that community. So we're really looking at a very different scenario than previous people have done. So let's get on to a bit of the theory. This is where the math comes in. Here's the basic thing, right? These 3 techniques here, these are the 3 techniques where people have really studied up and trying to come up with how do you do single unit, batch of 1 active learning. What's the theory for that? The first thing you need is a measure of model confidence. And let's say, how confident are you that this is a good model? How sure are you that you have the final model, the best model for your kind of performance? Maybe that's errors, maybe that's precision at a fixed recall, you know, whatever your metric is. So do you have a good model for that particular performance? What's your confidence? And we're going to measure it where lower is better. Now we're going to put a 1-step look ahead on that. right? So this is our current confidence. This is our future confidence. If we've got our data set L and we've added a new data point to it. So this is our future confidence with another data point. But the fact of the matter is we may suggest a data item X, but we don't know the label, right? That's our problem. So what we're going to do is we're going to average over the probabilities of the label under our current best estimate model. So we average over the probabilities of the label under our current best estimate for how confident we'd be in the model were we to get a label. And we put this together, we get a difference in confidence, an expected difference in confidence. And that's the measure that these three share. The measure I figured out about 15 years ago. Now, bold is where we put an entropy on that on our model. And the trouble is it's an entropy on our model parameters. In Moku is a bit smarter. And let me explain this. This is the thing that's important, right? This says how much error do you get when you use your current best classifier on this new data X? This says how much error do you get when you, on your new data X, do you use your hypothesis? So this is your best classifier, and this is your hypothesis. The error for the best classifier, because it's a best estimate currently, probably should be higher than the error for the actual hypothesis, which is assumed to be the true value. And in fact, you can show with a bit of math that this is greater than zero. But that's what this measure of confidence says. The measure of confidence says how much error are you losing because you're just using your current best guess from the data as opposed to knowing the true error. How much error are you losing? That's our error-based confidence. This is our parameter-based confidence. And if you plug these into this formula here, you get an active learning formula. Two problems with this: the bald one, which is the Bayesian active learning, it's only telling you uncertainty in your parameters. It's not telling you uncertainty in your model performance. That's what you want. You want your model to perform well. It doesn't matter if some of the parameters are a bit funny. It really matters about your performance. Whereas the problem with Moku, which is published this year, it's presented at ICLEA, it's a new paper. It only applies for classification errors, right? It's being developed for errors. And remember my statement earlier, we don't care about errors. No, it's not a problem for any of our active learning tasks. We have other problems. So we're going to have to change these. This one we know is just too general. It's not addressing the right problem. And this one is very specialized to a minimum errors task that we don't care about. So we're going to have to improve on these. I just thought, well, you know, Moku's using something called Bayesian regret. I didn't explain that, but it is. And something I thought, well, it's similar. I'll use a scoring rule. Now, for those of you who've used deep neural networks, the scoring rule is the loss function that you pass off to TensorFlow to optimize your system. You always give it a loss function. And that is the statisticians call it a scoring rule. And there's a property that if you use what's called a strictly proper scoring rule, it's got a lot of nice features. And what I can do is wrap up a strictly proper scoring rule inside the same kind of formulation that, so I can put my strictly proper scoring rule here with something, and then I shove that Q that I get into here, and hey presto, I've constructed a new active learning metric. So, and these are some proper scoring rules I can use. One of them is least squares. The other one is log probability, which is the most commonly used scoring rule there is in deep neural nets. It's the one all the classification people use. But this is the one we like. This one was a bit general, I thought. We use this one in all our experiments. And there it is, wrapped up into that Q function. There's the general formula for the Q function, which is a bit more general. I won't do a breakdown of this now due to time. But here it is once I simplify. This is my new Q function, which is has some relationship to the one we saw for Moku. It's got different bits and pieces in it. Certainly this expectation out the front is the same. And we get a lovely theorem for that, that if we use these Q functions, the resulting active learning algorithm will converge to the best model. So we know it's a safe active learning strategy to use. Anyway, we've done some experiments with this, and this is my just sort of final to show you a few things. Here we are running on the small IMDb data set. This is movie reviews. We're running here very small data sets. We give it 20 examples to begin with, and then we train with 50 more examples using our active learning. And our accuracy starts off at random, basically. 50% is random. It takes a while to learn this task, but red is core MSE. That's our algorithm. A bit of a description here. Random is this brown one here. The original Moku that the guys published this year is this green one, which works quite terribly. The bald one is blue, but the weighted Moku is yellow, and yellow and red, that's their algorithm and our algorithm, pretty much identical, right? Same performance. We find this for accuracy on quite a few problems. Here we're looking at full MNIST. This is the, I think it's the zip code data, the number data. Full means the full 10 digits. Again, we're just using a small sample. We start off with 20 and then add our algorithm, and I'm giving the F1 here as well as the Bria score. So Bria score is the mean square error. Ours is the red, bald. The original Bayesian active learning using entropy is the bad one. It's blue, and the weighted Moku is the updated one that we're comparing against. We're beating it a bit in these tasks. So anyway, we've just really started these experiments. This is showing you some of the results. And that is the end of my talk. So what have we done? We've talked about the information overload problem. I've talked generally about some of the things we're doing to make that a working system, and that's very much some joint work with some of my colleagues here, like Dr. Landu. And finally, we've drilled down into this active learning thing where we're really trying to understand the problem. And I think it's really a problem that's not fully understood currently. So, but we're hoping to get there. So thank you for your time.
Thank you very much, Ray. This was fascinating. I think I'll leave you with Dr. Salman for questions now. And I have many questions myself, but let's start with Dr. Salman.
Yes, thank you, Yaqub. So first of all, thanks a lot for a very interesting, engaging talk. I will be taking some questions from the audience as well, but I would like to start with one of my own questions. So you mentioned in the active learning, one of the problem scenarios had this problem of, you want to learn in a continual manner, right? So as more data is arriving, let's say, if it's a medical problem, and then there are new reports coming in. So did you, consider any setting which kind of combines active learning with continual learning or incremental learning? And what are your thoughts on that?
Yes, this is, I really skipped over this, and that's the question, right? How do you mix them? And we're just starting to think about that, but I don't, the way we're looking at it is, I don't think it's anything new or novel. We're using what's called screening, and we've got this operating actually at an ambulance monitoring system in the city. We first off screen the data, and what the screening does with our algorithm, it says, oh, definitely positive, oh, definitely negative. Those get split up and the annotators never see them. We just give the annotators the uncertain stuff in the middle. And occasionally we give them the either side just to confirm we're on the right track and to get some sort of overarching statistics for management to see, so they can be comfortable that our system is operating the way it should. But in general, so you're using the confidence of your model, and your model has to report a calibrated confidence. And with that, then you can split the data up, do the filtering, and now it's not so much active learning as much as it is feeding annotators the right data. And our research here, which we haven't got to yet, is we want to give the annotators heads up. So we want to say, underline the drug names, highlight the sections that imply, say, self-harm or suicide or something like that. So that's the future work there. And this is the same problem, whether it's no matter if you're working with, say, medical experts, X-rays, whatever it is. Yeah, but you've got the right question there. That's it.
Yes, thanks a lot. So you also mentioned BERT models, and you mentioned that, as we all know, they have very poor data efficiency, right? So they need a lot of data to train on. So you mentioned that you have been working on reducing the amount of training examples that are required to train a BERT model. So can you please tell us a little bit more about what are the tools or mechanisms you're exploring, towards reducing or improving the data efficiency of BERT models?
So I will clarify, we don't have the computational power here to do any real BERT research, right? I mean, and if you're doing reviewing, you'll see the distinction between the big lab reviewers and the poor academic reviewers. The big lab reviewers know heaps about running loads and loads of experiments because they can do that. And there really is it really is two sets of groups. We can't do that kind of thing, where what we're doing really is trying to harness BERT in a way so that we can use less data. And one thing we do is, where we don't ever fine-tune BERT, all we do is we fix the BERT layers, and all we're tuning is the upper layers above that, the say 2 RNN or the single layer network or something that is above the BERT layers. If you have maybe more than 500 or 1,000 data points, we may do a bit of fine tuning, and actually remarkable how important that is, but it's very slow, like you say, and it does slow things down. But in the context we're doing, we have a bit of computation time in the real problem to do a bit of retraining like this. So it's not a major issue once we get things working. But in our experiments, it is a major issue. And we have the two cases where we don't retrain BERT, and less often we will retrain BERT. We have to set the flag to let the fine tuning go on. One thing we haven't experimented with is doing the full self-training on BERT because we have a lot of unlabeled data, right? We've got gigabytes, 100 million records or something of unlabeled data. So we could do self-training on that. We haven't tried that yet. And I think that will be very important to get to, but that's not labeled training. Anyway, yeah, so I do have to qualify where we're not doing fancy tricks with BERT because we can't, we don't have the computational power. So.
Sure. Thanks a lot. So we'll just finish off with one last question, and probably Dr. Yaqub can have this question. So you mentioned strictly proper rules. I was wondering, like, what qualifies to make a loss function strictly proper scoring rule?
So the Wikipedia page on this is pretty good, actually. Where have I got this? Oh, it's down here. Is describes it well, but basically it's got to be a continuous function. Let's see what they say, actually. Characteristics. There's something about the derivatives, and I forget the details. But the best known examples are the log one and the mean square error. There's a few more they do. But it must have the case that the optimal solution is always a minimum for the rule, and also that it's differentiable in terms of the parameters. And any discrete rule like errors is not differentiable, so it can't be a strictly proper rule. So I'm not answering your question very well. I used to know this once upon a time, but I'll say the Wikipedia page does a good job of this. And this is something we usually learn in I think it's like third year stats course, which is pretty, gets pretty a mathematical stats course, and it's rarely something people would do in machine learning, but the more theoretical machine learning people are familiar with it. So.
So can I ask a question about uncertainty? So you mentioned that there's uncertainty in the model parameters, which you probably don't care too much about. There's uncertainty in the accuracy that you probably care more about. But what about uncertainty in labeling, in the mechanical Turk, especially in applications such as medical applications? Is that something you've studied before?
Yeah, this is another whole issue. So there's sort of a way of like throwing this problem away and sort of ignoring it, right? And what we do is usually we have this notion of inter-rater agreement. And that's a standard notion in the social sciences and the medical sciences. And you measure the inter-rater agreement. And so if any two different experts agree on about 80% is pretty good. On our ambulance data, they get about 90%. 95%. So it tells you, once you know what the inter-rater agreement is, it tells you what the error rate is intrinsic in the data, and how hard the problem is. In the X-ray world, it might go up to 95, 97, but it can be lower. And you measure that, and that's going to tell you you can't get better than that, right? Of course, we will, when you apply a good learning algorithm, it'll give you an extra percentage because it's learning from the different experts and kind of combining their knowledge. And so that was first demonstrated, I think, at Stanford with classification of breast cancer images a couple of years ago. But we call it super classification, where the machine learning system works better than the experts above the limit set by inter-rater agreement. But that's how we deal with that problem. Inter-rater agreement sets an intrinsic error rate that really you can't beat because you just don't know any better. And many problems have that there. A few problems, there are some science problems where there is a known correct classification. Well, for instance, in breast cancer there is, because people do surgery. They do surgery and they find out, but that's a bit of a expensive thing to do, so dangerous too. So usually in the medical case, if they have that extra test, then they do get the real performance. But usually in the data sets we work with, we wouldn't have that. So what I'm saying is we kind of steer clear of the error problem by saying, oh, there's a fundamental limit. We can't get better than that. That's the inter-rater reliability. Sort of deals with it. But and as you kind of guess, yes, a good machine learning algorithm will overcome that in a sense, and we haven't ever thought about trying to code up that in some clever way. Maybe there's a way of doing it. It's an interesting problem.
I completely agree with you. I mean, I had this myself with data, especially with ultrasound data, where, to be honest, inter-rater was no more than 70% in some cases.
Wow.
And that's the best you can do. But I would love to see solutions to this, because I'm not sure if we can do better.
It's a theoretical problem, and it may be the case that you can't do better with the devices we have, and you need that surgery to solve the problem or something, and that's intrinsic to the medical world, right? That's why they have a screening test and a confirmatory test.
Thank you very much.
Yeah.
Back to you, sir.
Great.
Yes, if we don't have any questions, maybe we can move on to the faculty meeting, Professor Wray. So there is a meeting organized, just to have a discussion with the faculty members. So we can meet there. Thanks a lot for a very engaging presentation, and looking forward to seeing you in the other meeting. Thank you.
Thanks a lot. Thank you. Very interesting.
So I'll skip out and jump into the other one, right?
Yes, please.
Yes.
Yes. Okay. Thank you.